So welcome Level 2 NCA Chemistry to the new internal quantitative analysis, the analysis of how much. This lesson will focus on Part A relating to titrations. So in order to appreciate the glory of quantitative analysis, you must become familiar with something called the mole. Now the mole is not a furry rodent that lives under the ground that causes problem with gardening. It is a very important concept in chemistry. All atoms differ in their mass, okay? And if you look at your periodic table, which we'll be using a lot in this unit, you will see that they have different molar mass numbers. In chemical reactions, we need to be able to add the required number of atoms or molecules or particles with other particles because we need a measurement of how much particles we have, not about the mass. Okay? Chemists have done this with a measurement called the mole. And 1 mole equals 6.02 times 10 to the 23 atoms of any element. This is known as Avogadro's number. And a mole can be calculated using the following formula. The number of moles, N, equals the mass, lowercase m, divided by the molar mass, big M, which is in grams per mole. The units of the mole are mol, mole. The units of grams is G, mass is in grams, G, and of course the molar mass is in grams per mole.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So in order to calculate molar mass, you have to basically add up the sums of all the atomic masses. So for our example here, hydrochloric acid, you just add the molar mass of hydrogen to the molar mass of chlorine, or 1 plus 35.5, to give the molar mass of hydrochloric acid of 36.5 grams per mole. Second example, water. So again, it's the sum of all the atomic masses, so it's going to be 2 times 1, which is the atomic mass of hydrogen, plus the molar mass of oxygen, which is 16. 2 plus 16 gives 18 grams per mole. So use your periodic table to find the molar mass of the following compounds listed 1 to 4, 2, 3 significant figures, and we'll go through it again in class. Okay, so back to calculating moles and getting familiar with the equation that we've just discovered this unit. So how many moles, I hear you ask, would you get in 20 grams of water? Well, again, this is the power of the equation. Number of moles equals the mass divided by the molar mass. So in this particular case, it would be 20 grams divided by the molar mass of water, which I've already calculated as being 18 grams per mole. So the number of moles is simply 20 divided by 18 to give 1.11 moles. Okay. Again, here are 4 examples. Here you can stop the video now, work through the examples, and then we will go through them in class to make sure you are on the right track. So, the mole. I want you to get into your textbooks and fill in the gaps from 1, 2, 3, 4, 5A, 5B, 6, 7, and 8. So pause the video now, copy those notes into your book, and then we'll go through them in class. So, number of moles equals mass over molar mass is very effective to determine the number of moles when calculating with solids. But I hear you say, what happens if you have solutions? Well, moles can be also used to calculate concentrations in solutions in chemistry. And this can be done using a new formula, C equals N divided by V, where C is the concentration of moles per litre, N is the number of moles, just as before, in the units of mole, and volume is the volume in litres. So, for example, what concentration is a solution when 2 moles of hydrochloric acid is dissolved in 50 mils of water? Well, the first thing you have to do is convert the millilitres to litres, and you do this by dividing by 1,000, or if you want to be a bit tricky, moving the decimal place 3 to the left, so that 50 mils becomes 0.05 litres. So now we have the information. We have number of moles equals 2 moles. The volume is 0.05 litres. So concentration equals number of moles divided by volume to give 2 divided by 0.05 to give the final concentration of 40 moles per litre.
You've got to give them more time. They can't do it this fast.
So here's some other examples I want you to calculate. Convert 0.5 moles of silicon tetrachloride in 500 mils of water, 3 moles of iodine to 23 mils of water, 2 moles of zinc carbonate in 2,000 milliliters of water, and finally 5 moles of potassium permanganate in 10 mils of water. Remember, for these examples, you have to convert grams into moles before doing any calculations. Okay, so here's an example here. What is the concentration of a solution of 2 grams of hydrochloric acid when it is dissolved in 50 milliliters of water? So first, we have to do conversion. So you're going back to the first equation we work with. Number of moles equals mass over molar mass. So number of moles equals 2 divided by 36.5 to give the number of moles of hydrochloric acid of 0.0548 moles. And then we go to our second equation where concentration equals number of moles divided by volume. So concentration equals 0.0548 moles divided by 0.05 litres to give a final concentration of hydrochloric acid of 1.1 moles per litre. So, an important aspect in chemistry is the idea of significant figures, because all chemistry calculations need to be reported to 3 significant figures in the NCEA in order to get excellence, which we should all be aiming for. This means there needs to be at least 3 numbers shown where a 0 is not considered significant, it is the first number. So here's an example here. So say you have the number, your calculator spews out the number 0.02367443. Well, in 3 significant figures, that would be 0.0237. Notice the second 0 does not yet count as a significant figure. Another example would be 0.50222222. Well, that would be 0.450 in significant figures, because the 0 becomes significant because it is after the decimal point. So I want you to look at the 1, 2, 3, 4, 5, 6 examples here and convert them to 3 significant figures. So pause the video now and then we will go through it in class. Okay, so welcome back. Another important aspect of the standard, I'm sure you're very familiar with it in maths and physics if you're taking those subjects, is that you need to show your working. The marker needs to be clear that you understand what's happening on with your equations and you are familiar with using the numbers that you are using in the equation. So I suggest you use the following format for this example. So what is the amount of moles in 36 grams of water? Okay, so you outline to them that the molecular mass of water is 18 grams per mole, and the mass of water is 36 grams. So you say the number of moles of water, therefore, will be the mass of the water, 36, divided by the molar mass of the water, 18, to give 2 moles of water. Okay, so here we have 2 examples here of A and B. I want you to work on A and B. I'll give you a little more time, so just pause the video now, work through those in your book. If you're having difficulties, come and see me later in class, but we will go through it in class also. Okay, so the whole direction of this is towards titrations. We're trying to find out the unknown concentration of a sample. So what I would do is I would create a table. Okay, and here's an example of a table you could construct where you have concentration on one side, volume, and then number of moles. So you have known, which is your K, and your unknown, and using the calculations you can determine the unknown from the known. So the mnemonic I use for C, V, and N is chocolates very nice. Okay. An important aspect also in titrations is dilution factors. So if the original solution was diluted before the titration, you could have to work out the concentration of the original by multiplying your result by that dilution factor. So for example, if your original solution was diluted by 1 part in 10, then you have to multiply your final answer by 10. So here's an example here. You have 25 ml samples of 0.442 molar nitric acid, and you require an average of 31.82 mils of potassium hydroxide to neutralize it. What is the concentration of the potassium hydroxide solution? And if the nitric acid was diluted by 1 in 20, what is the original concentration? What I want you to do now is pause the video and try and work it out using the chocolates very nice structure I gave you in the last slide. Okay, so here's further examples, which again If you want to pause the video now and get experience with it, working out these problems using the chocolate's very nice formula I've used previously. Okay, so now we're going to go into the actual titration experiment. So here we have the equipment that you will require. This is known as a pipette, which you'll become very familiar with. Okay, these are known as conical flasks, which you're probably very familiar with already from previous years at St. Peter's. This is known as a burette, which we will measure out your known or unknown concentration out in, whereas the known concentration will be in this liquid here, which will also contain something called an indicator, which will change color once the reaction is at completion. Okay, so the next few slides are a series of videos outlining the titration process.
The first step of any titration is to rinse the glassware. We start by rinsing the burette. Use distilled water or tap water to wash the inside of the burette. Release the water from the bottom of the burette so that you wash the tip as well. Pour the rest of the water out from the top of the burette, and as you do that, you wash the inside of the burette again. Now we rinse the pipette. The pipette doesn't have a tap at the bottom, so watch where you point the tip as you pour water in from the top. Make sure you wash all of the inside of the pipette. Now you're ready to start your titration. The second step of a titration is to prepare the burette. Rinse the burette with a titrant. Use a funnel to help you to pour solution into the burette from the top. Make sure the tap is closed at the bottom, or you'll have a puddle on the floor. Fill only a third of the burette and open the tap to wash the tip of the burette, just like you did with water. Pour the rest of the solution out from the top of the burette, cleaning all of the inside of the burette as you do so. Now you're ready to fill the burette with the titrant. Pour the titrant in from the top using a funnel. Fill the burette to the top above the 0 mark. Be careful not to overfill the burette. Now you need to release the bubbles from the tip of the burette. Do this by opening the tap all of the way and let the solution push the bubbles out. Let's see that again in slow motion. Watch the bubbles closely as they come out of the burette. Now you're ready to begin, so take the initial reading at the top of the burette. Make sure you read the bottom of the meniscus and record your readings to 2 decimal places. The third step of a titration is to use the pipette. Before you rinse the pipette, clean the outside of the pipette with a piece of paper. This is to ensure that you don't contaminate the solution when you put the pipette in. Now, rinse the pipette with the solution, using the pipette filler to suck solution into the pipette. Fill only a third of the pipette and let the solution wash all of the inside of the pipette. Now you're ready to fill the pipette with the solution. Ensure that the tip of the pipette is submerged under the solution so that you don't suck any bubbles up. Take the pipette out of the solution and adjust the level of the solution until the bottom of the meniscus touches the top of the line. Now transfer the solution into the conical flask. Take the pipette filler off and let the solution flow into the conical flask. Tap the tip of the pipette on the base of the flask gently to remove the last drop. You're now ready to start your titration. It's time to start your titration. The first thing to do is to add the indicator. Add enough so that you can see the color, but not too much so that the solution is opaque. Adjust the height of the burette so that the tip is inside the flask. Hold the flask in your dominant hand and use 2 hands to titrate, adding solution from the burette and swirling the flask simultaneously. Continue to add solution from the burette until you are near the endpoint. When you are near the endpoint, slow down the titration by adding the solution dropwise. When one drop from the burette changes the color of the solution, you are almost at the endpoint. During the titration, you might have splashed a lot of solution on the inside of the flask. Rinse the inside of the flask with distilled water. Continue to the endpoint, one drop at a time. Carefully add another drop from the burette and mix the solutions thoroughly. The solution is still slightly green, so add one more drop from the burette. You have reached the endpoint when no more green remains in the indicator. Add another drop to see if the solution remains gray or if hints of purple start to appear in the indicator. If it does, as in this case, use the previous reading as your final reading. You can always add one more drop to be sure. As you can see, the indicator has started to turn purple. Remember that when using screened methyl orange, the endpoint is a gray color with no trace of green.
Okay, so in a nutshell, this is the titration tips I suggest. Get both solutions together. In the big beaker, you put in the burette. In the small beaker, you're going to be dealing with the pipette. Remember to wash out the burette and pipette with diluted water, and also then follow with their solutions. Fill the burette and remove the funnel. Okay, so take an initial burette reading, which I'll help you with during our practical sessions. Then get a clean flask, which you've rinsed with distilled water, and then pipette 20 mils aliquot, which is an aliquot essentially is the amount that you're going to be placing from the pipette into your clean flask. Add a few drops of indicator. The indicator will depend on the substance that you're going to be testing for, and then titrate the burette solution into the flask until a faint color change is observed. Then you rinse the neck of the flask with distilled water and add a drop by drop from the burette until the color changes completely, and then you take the final readings. Okay, so you need to draw a table which you will record your titration results into, and that should be enough. So this is an example example here. Here's some results. Stop the video now and try and turn these numbers into 3 significant figures. Okay, and here are a couple of calculation problems that you should work on, and again we'll go through it in class. So there's the first problem and there's the second problem. There we go. Okay, so just a few last minute tips before doing the titration. Always remove the funnel before filling the burette, and always use goggles when pouring. Use white paper underneath the flask so you can see the color change. When pipetting, make sure you touch the tip of the surface of the liquid onto the flask, otherwise your number could be out by a drop or two. Record your results in a clear table with units, and do a rough shot first, give you a kind of a ballpark figure you can work around. Select 3 concordant results. So concordant means they're the same number or very similar to the same number, which are within 0.2 mils of each other. This is what you require for excellence, and only use these for your average. Other ones you just say they're outliers, you don't use them for your average. Convert milliliters to liters, remember, by dividing by 1,000, so conversion is important, and show all your units in your calculation. and round your last answer for your unknown concentration to 3 significant figures. So hopefully that helps, and you're all going to get excellence for this practical aspect to the internal. So here are the answers to all the activities which were in the video. So you can pause it now and go through the answers. Just check if your learning was correct. Further answers for the different slides there. And the answers for slides 12, 13 and 14. Slide 19, the table there. And finally slide 20, the problem involving problem 2.